So welcome back to part 2 of lecture 23. So I have kind of where we left off last time. We have our eigenvalues, we have our linear operator, so we have this part and this part of the theorem, but we still don't actually know the multiplicities of each of our eigenvalues. So let's first compute the multiplicities of each of our eigenvalue. And so here we're going to use kind of some math 1B03 results to capture this information. So remember from the definition that the multiplicity of an eigenvalue is the dimension of the generalized eigenspace. Okay, and that is equal to the dimension of the null space. So the dimension of the null space of the linear transformation t minus lambda to the I raised to the power of the dimension of v. That's how we defined it. And so the next thing that we also need to do is notice that this is the same thing as the dimension of the null space of the matrix that you get of the corresponding linear transformation raised to the dimension of V. So this is actually, we're looking at it as the dimension of the null space of the matrix. We're kind of back into math 1B03 land. And if you remember what that is, this is equal to the number of free variables in the matrix MT minus lambda I dimension V. So you have to figure out, take this matrix here, put it into row reduced echelon form, and then you can compute the number of free variables. Okay, so let me show you how this works by looking at our two distinct eigenvalues. Okay, and when you're doing this example, you definitely want to be able to have a computer program handy because the example I picked, it kind of blows up very quickly. Right, so from what I just wrote up above, the multiplicity of this eigenvalue is a dimension of this eigenspace. And the 4 here comes from the fact that the dimension of C4 is 4, because that's our vector space, C4. And we want to look at this matrix right here, the matrix of the linear transformation minus 10 minus the identity operator. And that's the same thing as taking the original matrix and subtracting 10 times the identity matrix of size 4, raising it to the power of 4. Okay, and so just to kind of remind us here what this is in the inside you would get 0, 7, negative 7, 15 minus 2, 0, 0, 0, 5 minus 5, 0 minus 4, 15, 1, and 0, 10, minus 5, and 15 raised to the 4th power. Okay, so just let me slide over here so you can just see where this matrix comes from. It comes from this matrix here, but I'm subtracting 10 from every entry on the diagonal. Okay, and now I want to crank this out to the 4th power. So this is definitely where you wanted to have a computer handy to crank it out. And then you want to row reduce the matrix. And when you row reduce the matrix, you end up with the matrix that looks like 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0, 0. Okay, and so the multiplicity of this eigenvalue is the dimension of this eigenspace, which is equal to the number of free variables in the above matrix. And notice that these are all the leading ones, right? All the underlined spots are the leading ones, so there's only one free variable. So the multiplicity of lambda equals 10 is 1. Okay, so let's do the same procedure for lambda equals 20. Okay, so for the other eigenvalue, what we need to do is find the number of free variables in the matrix that you get of the linear transformation, minus 20 times the identity raised to the 4th power. Okay, so here's the matrix that we get, and I'm raising it to the 4th power. So this is the matrix I get by subtracting 20 from everything down the original matrix. And I raise it to the 4th power, Again, I have a trusty computer. I use Octave to do this for me. So I get again, a 4 by 4 matrix where the top row has numbers, but all the other entries in the matrix are 0, and I can row reduce that, and I get 1.3, negative 1, 0.3, 0, 0, 0, 0, 0, 0, 0, and all zeros everywhere. And what I need to do is I need to compute the number of free variables in this, and I only have one leading entry, so the number of free variables in this case is equal to 3. So the story so far is that we have lambda equals 10 is an eigenvalue of multiplicity 1, and we have that lambda equals 20 is an eigenvalue of multiplicity 3. So the theorem says that we can find a basis such that with respect to this basis, we can write our matrix MT in the form of 10, 0, 0, 0, 0, 0, 0, 20, 0, 0, 20, and that's a star, and then we have star, 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 and 20. Okay, and so this is our 1 by 1 matrix, right? This is 1 by 1 coming from the multiplicity, and this part right here is 3 by 3, and that's coming from the fact that the eigenvalue 20 has multiplicity 3. So these are our two blocks, okay? And so that's what the theorem says, okay? So just to kind of go back to the theorem, it says that, okay, if you know the eigenvalues of your linear operator and the multiplicity, you can write it as a bunch of blocks where the number of times the eigenvalue is repeated is equal to the multiplicity. Okay, and so that's exactly what we have so far. So this is the story so far, but the problem is the theorem says that there is a basis, right? But what exactly is this basis? And more importantly, can we fill in the stars, right? So, but what is the basis and what is the stars? Can we actually fill this in? So obviously there's some more work to do. Okay, the theorem says we can do this, but now let's go try to figure that out. Okay, so in the next part, we'll start the next stage of kind of trying to fill in some of these gaps.